Welcome back. In the previous class I was talking about higher order sliding mode control. Particularly I was discussing about twisting and super twisting. So both algorithm belongs to second order sliding mode control. Now one question is very important, how to extend for same kind of algorithm for third order, fourth order or any higher order. Answer is not straightforward. It is possible to show that if you have third order system and same like twisting, if you take 2 gains and 2 switch, if you extend for 3 gain and 3 switch, then convergence become very difficult, and due to that reason some alternate solution is required. In this particular lecture I am going to show you the alternate solution. So main purpose of discussion, I am going to introduce one of the idea where it is possible to show that using continuous control you can able to realize any order of sliding mode control. Okay, because one of the important requirement whenever we are introducing the higher order sliding mode control, to generate sliding mode directly to the equilibrium point, and we are maintain the continuous control. So several discontinuous control that we are going to discuss in the subsequent lectures is proposed by the Professor Levant. Although the algorithm which is proposed for the higher order, that is very limited in the literature. Now in this lecture I am going to show you that just using very simple idea which is proposed by Professor Levant, one can able to realize continuous control for the any order system, and this is particularly the contribution from the India side under the guidance of Professor Vigyan Bandyopadhyay, that how to realize continuous higher order sliding mode control for any order system. Okay, and these classes of sliding mode control is also called 5th generation sliding mode control, and somehow it is able to solve several problems which is actually commonly occurring in the industry due to discontinuous control. So let us start the lecture. So main idea to introduce the notion of continuous integral sliding mode control. So you have already understand what is meaning of integral sliding mode control. So main idea, what basically we are doing, that whenever we have system, so we are going to start sliding from initial point onward, there is no reaching phase. Suppose that if I have second order system, so I am going to start sliding from here and I am going to maintain. In this way the role of the sliding mode control is to just reject the disturbance, and now whatever control we have learned during the previous modules, integral sliding mode control, that is discontinuous because that is based on the first order sliding mode control. In this lecture I am going to first tell you that how to actually extend that algorithm such that using continuous control you can able to realize same kind of phenomena, and obviously I am going to utilize the beautiful property of the super twisting algorithm, and it is possible to show that super twisting algorithm has also same property like first order sliding mode control. It is also able to not only able to reject the disturbance, also one can able to estimate the disturbance. So that property I am going to utilize, and after that I am going to design the any arbitrary order sliding mode control. And obviously we have verified the algorithm on some kind of electromechanical system which is actually available in lab of IIT Bombay, system and control lab of IIT Bombay. So using this particular, what is learning outcome? Learning outcome, obviously we are trying to understand the limitations of the classical sliding mode control, and after that we are trying to introduce the notion of arbitrary order sliding mode control based on the continuous integral sliding mode control. So obviously whatever algorithm that I am going to utilize, that is actually super twisting algorithm. So before going to understand the further concept, let us try to understand the notion of the higher order sliding mode control, just revise the notion. So what we have seen in the previous classes, suppose I have system like fx multiply gx into u, and after that if I have y equal to sigma x, and suppose that if I want to maintain sliding along this output variable, then what basically we are doing, how basically we are defining order, we are taking the first derivative. So after taking the first derivative, if control will not explicitly appear, then we are going to proceed for higher order derivative, and in this way whenever we are taking the rth order derivative, at that time discontinuous control appear. Okay. So now what is our goal? To design some kind of discontinuous control U discontinuous such that sigma 1, that is first derivative, up to sigma r minus 1 all equal to 0 in finite time, and after that sigma r should, solution of sigma r or solution of whole this set is understood in sense of the Filipov. So in order to maintain second order sliding mode control, what we have to do, I have to take second order system, some kind of second order uncertain system where that will represented by phi, and some kind of psi where phi and this both are uncertain. Now I have to design some kind of discontinuous control. So based on that, basically we have designed the first control, that is called super twisting algorithm, and super twisting algorithm is only applicable for relative degree 1 system, although this is second order sliding mode algorithm but applicable for first order system. It means that if you take system like x dot equal to u, and if you design u, first term is this and second term x2 is integral of this. Okay, and obviously here I am assuming disturbance dt, finally this is converted into form of rho like d dot t after taking some kind of transformation. And how basically we have proved the convergence of this algorithm? We have proved the convergence of this algorithm using some kind of a state transformation, and after that now using algebraic Riccati equation it is possible to show that if I design gain k1 and k2, then it is possible to maintain x1 and x2 both equal to 0 in finite time. So that kind of things we have already learned. So let us try to see that what is idea of the integral sliding mode control. This is a classical integral sliding mode control that is actually coined by the Professor Utkin. So idea is, suppose that if x belongs to R, if I have one dimensional manifold, so what I am going to do, I am going to design this kind of control, that is minus k signum x, and using design of this control it is possible to show that xt equal to 0 after finite time t greater than equal to t, and beyond that it is going to maintain. What does it mean? That x is 0 but x dot, instantaneous value of x dot is not 0, but it is possible to show that in order to maintain x equal to 0, the average value of x dot equal to 0. That is also called equivalent control method. So whenever you are going to calculate the average, then this term comes into picture. So one of the way to calculate average, just you can pass through low pass filter. So discontinuous term whenever pass through low pass filter, it is possible to show you can able to reconstruct the disturbance, and due to that reason whenever you are going to add classical sliding mode algorithm with any existing control, then this particular sliding mode control is going to taking care of all kind of disturbance after finite time. Now let us try to see the super twisting control. So I am going to start with exactly the same system. So our system is x dot equal to u plus dt. Now what I am going to do, I am going to design the super twisting controller. So first term is k x1 power half. So a scaled value of proportional control you can able to assume like this, and after that I have told you that this is nothing but some kind of integral, because v is used here and v dot is defined here. So this is acts like some kind of integral where only sign information is used. So due to that reason this is non-smooth PI kind of controller. Now once you utilize here, and if you convert in some kind of fictitious variable z, then it is possible to show that if dt is differentiable. So that kind of assumption I have. So that kind of assumption is not here. You can see in the previous slide I am assuming that just d is bounded. So supremum of d is bounded by some d0. But here whenever you are going to apply the super twisting algorithm, then at that time there is no condition on bound of the d, just you have to assume that D is differentiable, but now condition on D dot that comes into picture, that supremum over all T that should be greater than equal to some known value, that is here I am assuming delta. Same condition I have basically retained like this. Okay. Now you can see that since D is differentiable, so finally algorithm will converge like this, converted like this, and this gain, this is optimal gain, I have already told you, that is given by Professor Levin. So if you select this gain, then it is possible to show that x and z both equal to 0 in finite time. Okay. So since x and z both equal to 0 in some finite time t, so it is possible to show that z equal to v minus d. So d equal to minus v, and in this way I can easily able to calculate the disturbance. There is no need of the first order filter. Okay. So in this way you can able to reconstruct the disturbance. Now let us come to the higher order sliding mode control. So what we have seen, input output linearization, what is our observation? Whenever system like x dot equal to fx plus gxu, and if I have to maintain y equal to some sigma x, so after that we are taking the subsequent derivative, and finally what happens, suppose that order of relative degree of this system with respect to sigma x is n, then at nth derivative control is explicitly going to appear. Obviously here I have written there is no uncertainty or no other term associated with control. So in ideal case it might possible that non-linear system is completely converted into non-linear system in framework of the output and their higher order derivative. Okay. So this is called completely feedback linearizable system. So suppose that if I have completely feedback linearizable system, then it is possible to show that you can able to design some kind of state feedback control, and that state feedback control structure is given like this, and by pole placement method it is possible to show that if you design k1, k2 and kn, then x1, x2 up to xn, that is tending towards 0 as t tending towards infinity. Okay. But here our requirement is little bit more. What I want to design control such that all state x1 up to xn, that is 0 in finite time. So for that what we have done, we have utilized the concept of weighted homogeneity. Okay. So obviously this is linear system, so this is homogeneous. Now I am going to utilize the concept of weighted homogeneity. So what I am going to do, I am going to scale x1 by some kind of weight, that is x1 power alpha. Okay, that kind of weight means lambda power alpha x1, sorry. So I am going to give this kind of weight lambda power alpha 1 x1. Similarly x2 I am going to actually scale that lambda alpha 2 x2. In this way I am going to give the weighted homogeneity, and then it is possible to show that if you scaled x1 like this, so obviously if you put lambda power alpha 1, so what happens, that automatically if x1 is scaled by lambda into x1, and if you substitute here, then lambda power alpha comes into picture. What is significance of this term? This term is just maintaining the sign. If you are calculating absolute value, then obviously x1 is positive, negative, then same sign, and due to that reason we have added this kind of term. Okay. In this way it is possible to show that if you modify the classical feedback control by homogeneous feedback control, and if you maintain alpha that lie between minus epsilon to 1, then, and if you maintain the alpha 1, alpha 2, alpha n, where alpha n plus 1 equal to 1 and alpha n equal to alpha you can select between this, then it is possible to show that by choosing the gain using this Hurwitz matrix, all state x1 to xn are finite time stable. So this kind of things you can easily able to show. So this result is actually taken from the Bhatt-Bernstein paper, and paper name is geometrical homogeneity. So now you can see that what I have done, I have constructed control for second order sliding mode second order system. So our system is x1 dot equal to x2 and x2 dot equal to u, and after that I have taken some kind of disturbance. So first I have constructed control for disturbance free system. So if I am going to construct the classical control. You all are already well aware that classical state feedback control looks like this. Now, how basically this is different from classical state feedback control? Now, I have a scaling term here and here. Okay. So, due to this scaling term, it is possible to show now that x1 and x2 equal to 0 in finite time provided there is no disturbance. But once disturbance comes into picture, you can see that I have taken this time varying disturbance. Now, you can see that I am not able to settle on the equilibrium. Okay, what is equilibrium point? X1 equal to 0 and x2 equal to 0. Okay, so that is deviated. It means that in presence of the uncertainty, the feedback controller which is proposed by Bhatt and Bernstein is not robust, okay, or at least not insensitive with respect to disturbance, you can tell. Now, what I am going to do? I am going to modify the previous control such that it is possible to show that in presence of uncertainty also that will work, and that is somehow the basic idea of the second order sliding mode control or higher order sliding mode control. Now, what you can do? So, simply sliding mode control is suggesting, suppose that now you have some kind of u and after that some class of uncertainty. This uncertainty may be state dependent or time dependent uncertainty. Now, you can design some kind of discontinuous control here. What happens that whatever uncertainty I am going to keep inside this disturbance term, it might possible uncertainty may be depending on control also. Okay, and after that now, if you see this system, so this is free from the disturbance. Now, I have to design discontinuous control, second order discontinuous control such that I can able to achieve sliding mode control. Here control is continuous, so obviously I cannot able to interpret that kind of result in flip-flop sense. Now, if you remember the class of integral sliding mode control, at that time what I am telling, you have to design two control. One control which will act in the absence of disturbance. Okay, and obviously whenever we are talking about sliding mode control, only we are talking about matched uncertainty. What is meaning of matched uncertainty? Those class of uncertainty which will enter through the control channel. Now, what you can do? You can design some kind of control that we have given name as a U nominal control. Okay, so once you design U nominal control for the system when there is no disturbance, then this become U and N means normal. Okay. Now, if you solve it, then it is possible to show that this kind of solution comes into picture, and since xt is original, so in presence of the uncertainty, this solution xt and this in absence of uncertainty, that is not going to match, and due to that reason what we have done, we have multiplied with g because here u belongs to Rm. So, finally sliding surface should belongs to Rm. So, how to do that? How to match? How to map to this particular xn, because xt is belongs to Rn to Rm. So, for that I have actually multiply with this kind of projection matrix. Okay, suppose that if I have u belongs to R in case of the higher order sliding mode control, just I am assuming initially that I have some kind of chain of integrator system and u belongs to R. So, using one control I am trying to stabilize whole system. So, at that time you can easily able to take this matrix G in such a way such that again ST belongs to R. Okay. Now, what was the idea of the classical sliding mode, classical integral sliding mode control? You can add discontinuous term, and after that if you have m number of component, so component wise you can design this algorithm. Okay, and using that it is possible to show that finally you can able to make sure that u discontinuous is exactly equal to the value of the disturbance. Let us try to see for the second order system, then things become more clear to you. So, for second order system, suppose that if I apply nominal control to this whole system, okay, so only this part of trajectory is affected by disturbance. So, if somehow I will actually estimate this disturbance and compensate, then whole system is governed by the disturbance free way. It means that nominal control is going to act on this whole system, and due to that reason you can see that what I have done, I have constructed sliding surface just based on the last subsystem. So, what is solution of last subsystem? U plus D, and U is containing two part, U nominal plus U discontinuous. So what is role of U discontinuous? The role of U discontinuous to estimate this disturbance as well as compensate this disturbance. Okay. Now if you calculate S dot, then I have U plus D minus D nominal. D nominal is coming from here because here x2 dot, so x2 dot equal to U plus D, and x2 0 is constant, due to that reason derivative is 0, and after that this comes into picture. Now if you design U equal to U nominal plus U discontinuous, you can see that U discontinuous, I have selected this, then it is very easy to show that average value of S dot equal to 0 during the sliding, and due to that reason I can able to confirm that U discontinuous equal to minus D. So now here I have two part, control equal to U discontinuous plus U nominal. Okay. Now if U discontinuous is exactly equal to the disturbance during sliding, so our whole system is governed by the nominal control, and that is the idea of the basically integral sliding mode control. Now U nominal you can design by Bernstein control method, and in this way you can see now that what happens, that I will get exact convergence. It means that now all property of higher order sliding mode control is satisfied. I have U equal to dt, so I have disturbed system, I have design control. So first part of the control, that is the continuous control, that is designed like this, and after that second part of control, if you see carefully for this second order system, that is discontinuous in nature. Okay. So basically overall control is K1 x1 power 1 by 3 signum x1, and after that K2 x2 power half signum x2, and after that K3 and signum, and inside signum now you can see that this whole S comes into picture, and due to that reason now I have discontinuity at the x2 dot. So using Filipov method I can able to prove that x1 and x2 both equal to 0 in finite time. Why? Because this term is only responsible for taking care of disturbance. Finally whole trajectory is governed by this kind of finite time controller. So finally I will get the finite time stability. Now what is problem is with this controller? You can see that control is discontinuous. Now what I am going to do? I am going to utilize same idea, exactly same idea. Now in place of the discontinuous control I am going to add the continuous control, and you can see that how basically we have defined the continuous control. In order to define continuous control I am going to take the help of super twisting algorithm. Okay. So K4 S power half signum S, V dot equal to K5 signum S. S is exactly same like here. Okay, same like the classical integral or discontinuous integral. Now you have this kind of a structure. Okay, if you are going to take the derivative of S dot, basically how we are designing sliding mode control, we are selecting sliding manifold, and after that we are calculating rate of change of the sliding variable, and then we are maintaining that equal to 0 in finite time. So same way I have proceed, and after that again I have done the state transformation or fictitious state I have defined V plus D, and now you can see that if you select K3, K4 and K5, that is gain of the super twisting algorithm, this is nothing but super twisting algorithm, then I will get this. So what is idea now? That this USTC is going to taking care about this particular term disturbance. Okay. So now what happens, that whenever you have disturbance, so you can define, and if you have first order system, then you can define sliding surface just using this last term. Okay. And what is role of super twisting? Super twisting is going to actually taking care about this disturbance, and finally whole system is governed by the finite time controller, and in this way you can able to realize any higher order sliding mode controller based on the continuous control. Why? Because whatever U nominal, that is finite time controller, I have selected by the work of Professor Bhatt and Bernstein, that is continuous in nature, and this is USTC. So this is also continuous in nature. So combination of two continuous control is continuous. So same kind of things I am going to actually write here in form of theorem. So theorem is just extension of the Bhatt-Bernstein theorem. So how to select gain? Again you can select gain up to nominal control exactly like the Hurwitz polynomial, based on Hurwitz polynomial, whatever we have done in the case of the disturbance free system. And after that, now you have to select two more gains. So how to select these two more gains? Either you can apply the Levant gain criteria, or you can use the strict Lyapunov function that is proposed by Professor Morino, and you can select gain. Okay, and then you can design nominal control like this, and USTC you can design like this. Okay, it is possible to show that if you design sliding surface just based on the last state, okay, there is no need to involve all other state, just because uncertainty is here. So if somehow from initial point onward, if you are able to compensate the uncertainty, then our job is done, because what basically we are doing here, that we are maintaining S equal to 0 from a starting point onward, and due to that reason, from a starting point onward, disturbance compensation comes into picture, and due to that reason, the whole system is governed by the nominal control. Okay, and in this way, in presence of uncertainty, with help of some kind of here also in case of U super twisting, you can see that again now discontinuous term is going to appear in not on the nth derivative plus, but n plus 1th derivative. Okay, so n plus 1th derivative is v dot minus k n plus 2 signum s. Okay, so again I have solution in flip-flop sense, and in this way we can able to realize any ordered sliding mode control, and control is also continuous. So proof is again very simple, because what is our main intention? From an initial point onward, you can reject the disturbance. So for that you can utilize the notion of super twisting, that is continuous control, add it to the nominal control, and finally you can tune the gain either based on the Levant philosophy or Professor Morino philosophy, and finally you can able to show that from initial point onward, whatever value of the super twisting control, that is exactly equal to the disturbance, and system is governed by the nominal control, and overall control is continuous, where discontinuity is going to lie on higher derivative. Why discontinuity is going to lie on higher derivative? Because you can see that this integral term, so this is differential integral equation. So if you are going to convert into a differential equation, then obviously on a higher order derivative I have some kind of discontinuity. Now you can able to apply this kind of idea, even if here you can replace any kind of control. So I have just since I am talking about higher order sliding mode control, due to that reason I need nominal control, that is finite time stable. But suppose that if you are happy with the asymptotic stability, then you can design any control which is going to stabilize this nominal system asymptotically. But and you can also able to maintain the continuous control or overall continuous control. So you can define again sliding surface exactly like the classical classical integral sliding mode control, and after that now you can add one more term. Okay, so overall control, if U nominal control is continuous, then overall control is continuous. Okay, and after that you can select GB matrix equal to identity, and in this way you can able to proceed component wise, and then you can easily able to show that again S equal to 0. So disturbance is estimated and whole system is governed by the nominal system. So I have already told you that this plant is available in the lab of System and Control Engineering, IIT Bombay. So during our PhD, what we have done, we have implemented on this setup. Okay, so this is actually drive disk and this is load disk, and here we have some kind of idler pulley. So this arrangement of the whatever arrangement you are seeing here, belt, so this is rigid belt, but here we have two arrangement. One can able to change here flexible belt as well as the rigid belt. Okay, and based on that we have two different mathematical model. Okay, and how to drive the load disk? Using the actually drive motor, you can able to drive the load disk. Okay, so if you assume that this arrangement is rigid, then whole model is given by the second order. Okay, now obviously we have several disturbance because this is coupled system, so it is possible to show down, one can able to design the optimal control, LQR control, and in absence of disturbance one can able to stabilize x1 and x2. Okay, where x1 and x2 are the angular position and the angular velocity, and disturbance we have considered this. Now if you replace rigid belt by flexible belt, then this kind of mathematical model comes into picture. Okay. So, this implementation we have done with the one of our colleague Dr. Asif Chalanga. So, almost all continuous control we have developed with the Asif Chalanga. Now, he is working in industry. Okay. So, nominal control we have developed based on this particular LQR, linear quadratic regulator. If you are not familiar with LQR controller, so I have already recorded one course on optimal control, and that is available freely on YouTube. So, just type my name Shyam Kamal, you can able to find how basically this particular LQR controller comes into picture. Okay. And after that, now you can design U equal to KE, because I am going to solve the tracking problem, and USTC is nothing but the continuous control. Okay. And in this way you can able to design gain of LQR controller, and Q and R matrix you can select to design this gain, and after that this is the gain of super twisting controller. G matrix, this is projection matrix we set like this, and after that it is possible to show that flexible belt configuration we have used this set of gain. Now, this is the evolution of position during MATLAB simulation. Similarly, this is control, and this is evolution of the discontinuous control. So, in simulation you can see that once you replace classical integral, discontinuous integral sliding mode by continuous, then control become continuous, and obviously chattering will reduce. Okay. And this is again what we have done, that experimental result we have actually presented here. So, experimentally also you can see that efficacy is very good. So, our result is very close to the simulation result. And similarly, now flexible belt we have taken, and in case of flexible belt you can see that again control is continuous, and this is the experimental result. Now, it is time to conclude this lecture. So, what we have seen, that just idea of the continuous integral sliding mode control, you can able to define arbitrary higher order sliding mode control just combining the two methodology. One methodology that is proposed by Bhatt and Bernstein, such that if you have n number of chain of integrator, so how to design some kind of controller based on weighted homogeneity such that all state is going to 0 in finite time. Now, that control will not work in presence of disturbance. So, what you can do, you can add the idea of sliding mode control, that is basically the super twisting algorithm, second order sliding mode control, and adding these two idea, defining some kind of sliding surface, a specific sliding surface where disturbance comes into picture, and mathematically show that from a starting point onward disturbance is going to rejected, and due to that reason whole system is now governed by the nominal control, and in this way you can able to propose any order of the sliding mode control just using the continuous control action, and this is very good for mechanical actuator. So, with this remark I am going to end this class. Thank you very much.